This is video number 10 for the assembly programming and reverse engineering course. And in this video, I will talk about cache line split penalties, and memory alignment. A cache is a unit of memory that is built in the CPU. The most modern CPUs have 3 cache levels: L1, L2, and L3. L1 is the fastest and L3 is the slowest cache level. Each cache level has several cache lines, but the RAM does not have any cache lines. Then we have this example. So we define a quad word variable, and then we execute this instruction. So we copy the data from num1 into the rex register. And then the CPU checks if the data can be found in any cache level. This process is called cache lookup. It starts with L1 because that is the fastest cache level. If it can't find the data in L1, then it looks in L2 and finally in L3. And if the data can't be found in any cache level, then it will fetch the data from RAM. And after fetching the data from RAM, it caches the data in the cache line at a given cache level. That is useful because when the CPU needs to access the data again, then it can find the data in a cache line and does not need to look again in the RAM. And the CPU fetches the data always in 64-byte chunks, even when less data is required. That counts for the RAM and also for the cache lines. And yeah, if the CPU finds the data in any cache level, then it's a cache hit, and otherwise it's a cache miss. And after a cache miss, the CPU needs to look for the data in memory. Here's a cache line split penalty example, and here we have this memory address, it's a quad word, and this is the value that the CPU wants to fetch from a cache line. But we can see that the data, it goes through 2 cache lines. So it goes through cache line 1 and cache line 2. And that can happen if the memory address starts here in this example in cache line. If it starts at an address that is pretty close to the starting address of another cache line. So in this example, cache line 2. And then it can happen that the data is split across 2 cache lines. So if the CPU now wants to fetch the whole number, then at first it needs to fetch the data from cache line 1, then from cache line 2, and then finally it still needs to merge the data from cache line 1 and cache line 2, and then we have the full number. But the last steps, they wouldn't have been necessary if the data would have been aligned properly. However, cache line splits are only a problem when the code gets executed many times, for example in a loop. Otherwise, a cache line split penalty is not a big deal. It's also not guaranteed that a cache line split penalty occurs. How to align the memory addresses to share the data in a single cache line. Here's the data section, and this is the align macro. And with align 16, we can guarantee that number 1 starts at a 16-byte aligned memory address. That is not guaranteed for number 2, but if we want to guarantee that, then we can just type align 16, or if we want that it starts at a 32-byte aligned memory address, then we can type, for example, align 32. And here's the text section, but we will talk about that later. So at first we will talk about the data section. So number 1 is guaranteed to be 16-byte aligned, and under normal linker behavior, number 2 will then be aligned by 8-byte. And what is a linker? Here's an explanation in one sentence. NASM creates an object file, and the linker combines the object file with a .lib file, and then it creates a .exe file. Address alignment can be enforced or can be forced with an align macro. The number for the alignment needs to be a power of 2. Here are the addresses for 16-byte alignment, and this is how it looks like in our example. So here's address 16, address 0. Here is address 16, and that is where number 1 starts. And then at address 24, that is where number 2 starts. And here are the other addresses, and number 1 could also start at address 56, and number 2, it could also start at address 64. and their variables, they are in consecutive order, and that is also called spatial locality. So the CPU can now easily load all the data at once. And let's assume that the data is still not in any cache line. Then we execute this instruction. Move RCX number 1. And then the CPU needs to fetch the data now from RAM. It fetches always 64 byte. Since our data is aligned to share a cache line, the CPU needs only one memory fetch to copy the values into a cache line. So it copies number 1 and also number 2 into a cache line. Then we execute this instruction, move RCX number 2. So now the CPU can immediately load the data from a cache line. It does not need to look into the RAM again. When we should align memory addresses, if we execute any SSE or AVX instruction that requires memory alignment. And here's an example for some instructions that require 16-byte memory address alignment, and these instructions here, they require 32-byte memory address alignment. But yeah, just check the official Intel or AMD documentations, and then you will find more instructions that require memory alignment. And instead of using vmove APD, we could also use an instruction like vmove UPD. And the vmove UPD instruction works without aligned memory addresses. But yeah, there's no difference in terms of speed between vmove APD or vmove UPD when the memory addresses are aligned. However, if we use vmove UPD and the memory address is not aligned, then this can lead to a cache line split penalty. Guaranteed memory alignment. If we need to write any code that needs to guarantee memory alignment, then it's better to use vmove APD, because a not aligned memory address will then immediately lead to a program crash, while an instruction like vmove UPD would be able to keep executing the code, but with the disadvantage of the possibility of a cache line split penalty. So when we use vmove APD, then the program will tell us immediately that there is something wrong with our code. Then the last one, Windows x64 calling convention. Before function call, we need to make sure that RSP modulo 16 is equal 0. So the address of the RSP needs to be 16-byte aligned.